So today I'll be talking about flexible sensors, and the application that I'll be targeting would be wearable electronics and the robotics applications. So to be more specific, we will be trying to redefine the electronics and some of the sensors we have designed. So I will also be sharing with you all, and then the performance analysis and some applications we have targeted using those sensors, and in the end the way forward for this field. So we all know about the conventional electronics, and a lot of devices we have been using, but if we just talk about the transistor back in 1947 when it was invented, we know that how it looked, and its structure is pretty much same, but things have been minimized, and the performance of this transistor has also enormously increased. So that's the conventional electronics. But if we talk about today's electronics, it is, there is a huge improvement. If we talk about solar panels, smartphones, laptop through which I'm communicating with all of you, and a lot of other gadgets that we use in our daily lives. So there has lot of been features that we are enjoying because of this advancement in electronics, but still there are a lot of challenges, right? For example, the screen, my smartphone falls, the screen is brittle, so it can break. And in the same way, the main challenge is that these devices, mostly they are hard, they are rigid, and they have sharp hinges. So these are the challenges. These challenges also provide some discomfort when it comes to a patient who is in the hospital and he or she is looking for the diagnosis or continuous monitoring. Obviously, that patient has to wear a lot of devices, and mostly these devices are the sensors. And this point of time, most of the hospital, they all have these traditional ECG sensors, and they are quite hard, quite rigid, and obviously no one will try to wear those sensors if they have any other choice. Because of that, we have some target of redefining this field, where we can bring some new features into this field, so that we can design some sensors with better performance and some other attributes. So I would rather call this a wish list, I would say, that the devices should be comfortable. And here, comfortable mean that when you are wearing them, you feel good. They should be invisible, and invisible means that they are there in front of you, or when I wear those sensors on my body, they are there, but the material that I'm trying to use are transparent, right? So that they can hide the electronics parts. And similarly, it should be imperceptible. And here, imperceptible means that uh, you know it is there, but you cannot see. And in the same way, because all these sensors have a very close contact with a human body, that's why they must be biocompatible as well. And in the same way, they should be intuitive. That means it should be easy to use. And of course, there should not be any compromise with the efficiency of those sensors or generally the devices. So it's a wish list, and that's why a new field emerged in last couple of decades, and that's called the flexible electronics. And this field, obviously it's electronics, but here the devices, the sensor, the systems, they have been developed by the materials which are compliant. Like simply I can say the rubber type materials, right? So because of using these compliant materials, the devices that are being fabricated, they are mostly bendable, stretchable, or twistable as well. So if we introduce these features, what happens that we are bringing the world towards more safer, smarter, healthier, and simpler world actually. So a lot of applications are being targeted by this flexible electronics field, like consumer electronics, textiles, wearables, implantable electronics for improved medical and healthcare, and of course soft robotics. So I will just give you one example, which is, we know that every metal, if we talk about every metal wire, it has got some resistance. And the basic formula to calculate the possible resistance of that metallic wire would be that it is, of course, based on the material characteristics. For example, we have been studying that's the resistivity, which is constant, pretty much constant, and then the length of that wire, and the cross-sectional area. Now, in this picture, if you can see, what I'm trying to discuss is that let's assume that the cross-sectional area of these all wires is constant. The only thing is we are just trying to increase the length of wire. So, we know that the resistance is directly proportional to that length. That means if you increase the length of this wire, the resistance will increase. So, basically even a simple metallic wire that you normally hold in your hands, that's also a sensor, because if you keep on changing its length, it will change its resistance. But the problem is these metallic wires, they are hard and their stretchability is negligible. But somehow if that is possible, that if the same wire can be stretched, that means this can give you a lot of useful data. So that's why we bring those materials, we bring those innovations into the materials which can enable not only to the stretching property, but also on the same time they can give you the change in resistance or change in any electrical quantity. So here you can see the few sensors we developed, and this is quite bendable, it's stretchable, but on the same time the more you stretch it or more you twist it, the different data in terms of resistance, impedance, capacitance, or whatever the electrical quantity we are targeting, it will give you. So because of that, there are a lot of applications that we can target. For example, I can put on this similar sensor on my wrist. I can put the same sensor on the joint, and on the same time, because these sensors are intuitive and they are comfortable in wearing, that's why the patients or the people who are under continuous monitoring, they will not be disturbed, or at least there would be a minimum disturbance for them to wear these sensors. So anyways, so there are a lot of materials that are used to design those sensors, and if anyone is interested, I will definitely discuss, but I will try to give you a general overview that it's not only about stretching, but it's about stress, pressure, temperature, humidity, you name it. A lot of other quantities can also be measured using these kind of sensors. So it's not only about the strength sensor or a pressure sensor, but it's about whatever the quantity that is being measured, the sensor has to be flexible. The sensor has to be, stretchable, so that we can use on any part of the body or in any other industrial application, whatever it is. So generally, if you look at this picture, you will come to know that these flexible sensors can be used at different places on the body, right? So for example, if you want to monitor the continuous, you know, angle movement on your elbow, we can just place that sensor onto it. But just imagine that if you have a traditional, conventional, rigid sensor, obviously we cannot place that, because that will, first it will not give you the accurate data of your angle movement, but also it would be highly disturbing for that person who is trying to put on that elbow or any part of the body. So anyways, there are a lot of sensors like humidity, temperature, gas, light, and other, general sensors. But the main target is that it's not only just converting a conventional sensor into a, flexible sensor. Rather, we also have to work on its performance improvement. And when I say the performance improvement, it can be its sensitivity. It can be that the fabrication cost should be as minimum as possible. It should detect the wide range of that particular quantity, right? It should be fast enough, and the accuracy should not be compromised. It should be stable. It should be selective. So there are a lot of performance parameters which are used to, analyze the performance of any sensor. So of course, in any research or development process, not all these performance parameters can be improved. Rather, there is a trade-off, and that's what we have done over the period of time. This is just one result that I'm showing you, which is about the deposited PLGA, but I will just move it to the device fabrication, and I will discuss that as well. So this is reverse offset printing. When we printed the humidity sensor, so we use a state of art reverse offset printing using silver ink, and to to fabricate the comb like structure. But on that, we use a very simple technique, that is spin coating. We just deposited PLGA, which is polylactic glycolic acid, which is a famous drug delivery polymer, but we figured out that it has also humidity sensing property. So in the same way, this is a fabrication process for the strength sensor, and these are few of the samples that we produced, and this is the fabrication process for pressure sensor. This is pretty interesting. We developed this sensor using electrospinning process, and this is biodegradable, and it's a capacitive pressure sensor. And this was experimental setup. It's a custom developed experimental setup in which we tested a lot of humidity sensors, and it was pretty easy to use system. We had nitrogen gas to dehumidify this chamber. We also use a reference sensor just to compare our design sensor. So if we talk about its performance, it's was pretty good, and it was a complete range humidity sensor. And what do I mean about this is it can detect the relative humidity from 0% all the way to 100%, and its stability was pretty good, and it was highly linear. So then we also use the same humidity sensor in a breathing application, in which we just place this, because again I am saying it's a flexible sensor, so we just place that on the place upper lip, and it could detect even the very minute changes in the human breathing. So this is just a comparison, and it's again the custom developed setup that we developed to test the strength sensor by stretching it from 0% all the way to 200%. So, but our sensor was sensing up to 150%. So this is the simulation, because if you see that there is a common question that why you didn't created the straight channel, because we've optimized the design, and we proved that if we go towards the sinusoidal structure on the channel side, then the performance gets much higher. You can see there is amplification of surface pressure. So similarly, these are some results, and we tested this sensor up to 8,000 cycles, which shows that it's highly reproducible and it's also stable. And then we also, this is pretty interesting, that we use this sensor to detect the human drinking activity. The way you drink water, so there is a movement on this neck side. So we place this sensor, and we just try to prove that this sensor is sensitive enough that it can also detect subtle movements on your neck as well. And this sensor is waterproof, so we also tested in underwater applications. So this is another sensor we tested. This is a bendability test, that a sensor is under continuous bending force, but still it is able to sense the stretching. So these are other applications, comparison, and this is a experimental setup for a pressure sensor characterization. So it's again the custom developed in our lab, and that was used to apply the minute pressure under 5 kilopascal to test the capacitance as an output of the pressure sensor. These are the results, and the interesting thing about this pressure sensor was that it could detect as low as pressure of up to 5 kilopascal. And we also designed the snowboard based simulated images, on which we designed the 4x4 pressure sensors array, and it's completely developed by the lab, not commercially available. This snowboard is only the commercial item in that. So the good thing is that now you can see even a very small object, if you just put on that array, it can detect its shape, and it could also detect the wrist pulse monitoring. And as I told you that this is a biodegradable pressure sensor, so we tested it up to 20 days roughly, to see that if it is degrading or not, and it was successfully done. This is another work that we published. So this is optical sense, flexible sense, and it's again very interesting. We developed it a complete smart glove using our own sensor that we developed, and very I would say the pride moment for me is to mention here is that this entire project and published work that was published in Journal of Materials Chemistry, see, that's by my undergrad students. and they did a wonderful job, developed the application, and we also uh, you know implemented it on different body parts to see that this sensor is working or not. So this sensor is our own fabricated one, it's not the commercial one, and there are a lot of videos on this. But anyways, I'm just showing you that we could use the same glove to control a simulated now robot, right? So we design some tasks. So on different angles, our fingers movements, we could, activate a specific action by that robot. So yeah, again the sensors, the flexible sensor or soft sensor, I would say there are a lot of fields which converge together to make this field phenomenal and application oriented. So you need simulation, electrospinning, screen printing, reverse offset, 3D printing, electrohydrodynamic atomization, which is EHDA, a simple molding and casting. So there are a lot of fields, different fields, when they come together. So then we are able to design these sensors. So few other sensors I mentioned, but there are a lot of other types of sensors in the flexible sensors category which I haven't discussed. But as far as the conclusion is concerned, that you know right now the main target is that designing a flexible sensor is not a challenge, but designing a cost effective flexible sensor is a challenge. And in the same way, the biocompatible sensor. And the third one is the reproducibility, because over the period of time these flexible sensors, the structure or the material that we use or print or embed on its surface or even inside this channel, they start deteriorating, right? So and because of that the performance drastically decreases. So even right now we cannot say that this field has been in the level where we can say that it's up to the conventional electronics, where you can see the humidity sensor, which I mean, even after years, if you use a commercially available sensor, it still gives you the accurate information. But yeah, a lot of people from different fields, they are working on this aspect to make this possible. So yeah, that's it from my side. Thank you so much.